Welcome, Math 107 students, to the lesson activities for polynomial regression, which is lesson 22. The first activity has us looking at some data about a ball that's been thrown upwards with a velocity of 30 meters per second. We're looking at the height of the ball at various times. So quadratic regression was performed using our calculator or Geogebra. And we're using time in seconds as our x variable, which is our independent variable, and the height, y, in meters as our dependent variable. So let's label the axes on the graph above. We have, along the x-axis, we have time in seconds. And along our vertical axes, or our y, we have height in meters. Okay. We can see here we have our regression equation that was given to us from the calculator or from Geogebra. And let's write that down. Y hat equals negative 3.65 x squared plus 23.73x plus 3.76. Again, note the little hat on y helps us to remember that this isn't the actual data values we're getting, but estimates and predictions. Okay, so let's find the vertex of the regression parabola that's given by this equation and explain what it means in this context with this story. So we remember that the x value of our vertex is the opposite of b over 2a. In this case, that's negative 23.73 divided by 2 times negative 3.65. And that's going to be approximately 3.25. Now, if we look at our graph and we sort of estimate where 3.25 is, it might be about right there. And if we look up to our graph, we can see, yeah, that looks about where the highest maximum height would probably occur, right in that area. Okay, so we know that we got 3.25, and now we're trying to find the maximum height that goes with that time. So to find the maximum height, the y value of our vertex, we put in 3.25 into our regression equation where we see x, and we perform the arithmetic. Follow our order of operations, and we get approximately 42.33. Okay, now I think the answers may say 42.37, but the rounding has to do with how many places you carry out both your x value and also up here in your regression equation. If we put the full regression equation in with more decimal places shown, we probably would get the answer that's in the answer key, but 42.33 is okay. So what does this mean? Well, let's go back to our graph because I like seeing things. So what this means is that at about 3.2 seconds, the ball is going to reach its maximum height of 42.33 meters. And visually it makes sense, and we can see from our axes what each of those coordinates mean, what their units are. So putting that in a sentence, we're all probably going to write the sentence a little differently, but what's important is that we have both of these numbers along with their units in the sentence. So the ball will reach a maximum height of approximately 42.33 meters, 3.25 seconds after being thrown upward. Okay, now we may all say that differently, write the sentence differently. That's the wonderful thing about the human being. Again, what's important is you will see 42.33 meters somewhere in your sentence. You'll see 3.25 seconds in your sentence. But the other important thing is that somewhere in your sentence, anytime you talk about a vertex, there should be some word that describes, in this case, maximum, highest, maximum height, highest. If it were a vertex for a parabola that opened upward, we'd be talking about least, smallest. Okay, you have to have some type of language that describes the fact, in this case, that this is like the top height. It's the highest value in your range. Sorry about this little thing. I just must have hit the wrong button. All right. Do you feel this model represents the data well? What do you think? If we look at each of the actual data points and we look at the parabola, it appears to be a good fit because the parabola is fairly close to all those points. So I would say, yes, the parabola fits the data well. Okay. It's a pretty good fit. All right, let's take a look at another problem. Okay, table 2 gives the number of wildfires in the United States per year from 1996 to 2000. Now, we know that this year, 2017, there's been quite a few devastating wildfires in California. So it'll be interesting to see what this model may predict for 2017, if that was a question we'd want to ask. But we could ask that question. So the table below gives the number of wildfires each year. So we have 1996 up through 2000 for every year. And the number of wildfires here, the unit is thousands. So when you see 90, that means 90,000 wildfires. And what we're going to put into this table is some predicted number of wildfires based on our model. So label the axes on the scatter plot below and then use it to decide what degree polynomial would best fit the data. So let's label each axis. Now be careful here because you don't see 1996, 1997, 1998 up to 2000. What you see is 0, 1, 2, 3, 4. So 0, at 0, your y-intercept here is a number very close to 120. And here we go right here, we have 115. So it's clear that x is the number of years after 1996 or since 1996. In other words, 1996 is our base year. So you'd want to make sure that you realize that before you start using your regression model, so you have the right values for x. All right, so the graph is what told us that. So this first point here is 0, 115. In the year 1996, there were 115 wildfires. This point over here refers to 4, 123 says in the year 2000, there were 123,000. So you always want to check out your graph and your table to make sure you know what each of your variables are measuring. Okay, how many turning points are there on this particular scatter plot? Well, I only see one. I'm decreasing. Number of wildfires are decreasing and they're increasing. So I have one turning point. So what's the minimum possible degree we could use for a polynomial? Well, if you recall, n minus 1 equals the number of turning points with a polynomial graph. So since here n minus 1 is equal to 1, n equals 2. So we're going to use a quadratic regression to model this data. Okay, so let's take a look. First, we've got to label our axes here. So this is the number of years after or since, however you like to say it. What was the year again? 1996, right? 1996. And this is the number of wildfires in thousands. Okay. So we perform a quadratic regression in Geogebra, and we get the equation y hat equals 9.29x squared minus 35.14x plus 115.17. So let's use this equation to answer some questions. How many wildfires would this model predict for 2007? So let's see. 2007 is going to be an x value out here, if we kept going, an x value of 11 for 2007. So let's see how many wildfires we would predict using this model. So y hat, so x equals 11 because 2007 minus 1996 gives us 11. So we have 9.29 times 11 squared minus 35.14 times 11 plus 115.17. When we do a little bit of arithmetic, we will get the number of wildfires that this model predicts. So I'll give you a moment here to do a little bit of arithmetic, and you should come out with approximately 852 wildfires. I'm actually going to take the unit off here because we're just looking at the value of y hat. So you would write a sentence something like, always remembering you could use the word predict, or you could say according to the model, which would then tell your reader that you are using a model and this is a prediction. According to the model, there will be approximately 852 wildfires in 2007. Okay. My handwriting is getting worse and worse. Let's try a little clearer here. Wild fires. There we go. Okay. So according to the model, about 852 wildfires would be predicted. Okay. Do you feel this model represents the 5 given data points well? Well, let's take a look. The 5 given data points. Well, the only way to know that is to actually draw the regression equation based on this model, or actually write in the predicted number of wildfires for each of these. So what I'm going to do is I'm going to put this equation into my graphing calculator under y1. So let's see, 9.29 times x squared plus, oops, no, minus 35.14 times x, and then add 115.17. And then since our table here, it starts at 0 and goes through 4, I can ask the calculator. I'm going to set my table here, second table set. I'm just going to say 0 and increment by 1 because it's every year. And I'm going to have my table calculate all my values for the number of wildfires automatically. That's what auto means. So now I do second table. And now I get the number of wildfires predicted for each year. So let me pull this up. So at 0, or 1996, we have the prediction is 115.17. That's pretty darn close. You can't get much closer than that. Let me take a picture of this so that we have it without it keep falling off the screen here. Okay. So take a little picture of our data here from our calculator. Put it right here on the page. And we can close this calculator out. Do something. What do we want to do? Send it to a new page, send a current page. There we go. All right, let's put that up there. All right, so here's our table of values. At 1 or 1997, 1 year after 1996, it's predicting 89.32 wildfires. So remember, this is number of years after 1996, and this is number of wildfires in thousands. All right. 2 years after, it's saying 82.05. 3 years, 93. Wow, this is amazing how close these predictions are and estimates are to the actual data. And 4, 123.25. Wow. So you can't get much closer than that. That is, and if we actually drew the graph for these points, it would almost be on top of these values. So the data fits, this regression equation fits those 5 values extremely well. So we can see how close the predicted values are. Here's all of our predicted values right here, how close they are to the data. Okay, so you can fill that in using that language and write your own sentence that the model is almost totally perfect. In fact, I'm curious. I don't know about you, but I really want to enter this data into my graphing calculator and see what the R-square value is, to see how close it is. So, and we're not requiring you to do this, but this, if you're curious and you want to learn some of these new skills, and I'm just going to my catalog, second 0, to make sure my diagnostics turned on, because without that, I can't get my R-square value, which tells me how good the fit is. So I'm going to turn that on, and I have to hit it until it says done. And this regression is done very similar on that to the linear regression we performed a few weeks ago. So we 0, 1, 2, and it's not that much to enter, just 5 points. Okay, and then we'll move over and we'll put in the data for the number of wildfires. And hopefully 90, 81, 94, and 123. Now I'm going to perform, hit my stat button, perform my test, and we're going to go down now to quad regression. We tell our calculator where the data is, second L1, second L2, and this is the hardest part to remember. We want our equation to go into a y equals, so it's a y variable, so we hit vars, go over to our y variables, function, and y1. So now we do our, oh no, dimension mismatch. Oh, let me see what I did. Okay, let's go to it. Let's see, edit. Oh, okay, so what did I miss? 0, oh, I put in 1 extra year here. So let's go over here and get rid of that 5. Let's delete that. And now we should be all set. No panic. Let's see, go down to quad. We got to do this again. Probably don't mind seeing it again, right? Second L1, comma, second L2, comma, vars, y vars, function, y1. Enter. Oh no, I still have an error. You're kidding me. Now what's going on? Let me just clear all this out. Calculator. This is what happens sometimes, why my videos get so long, because I think of all these neat things to do, and before I'm not doing this video all over from the beginning. So hopefully I won't make any mistakes here. Vars, y vars. There we go. So you can see the equation that we've given you, the 9.28x squared minus 35.14x. Look at that R value, that R square value, 9.998. And this is what's always amazing to me. This is not made up data from a book. This is real live data that we're looking at. So it's not like we kind of fudged this to make it look good, right? This is the real thing, folks. So you can see how very valuable having models can be for making estimates and predictions. Okay, so let's see, send to new page, save on desktop, do something else. How about send to the clipboard? All right, and then we'll just paste it. There we go. So it's an incredible fit. So this information helps you down here. Incredibly strong fit for the data. Okay, so the next question is asking us to use some of the information we learned in the last few lessons about the leading coefficient test to determine the end behavior to the right for this model. So we're thinking about going into the future. Do you think this model will be accurate for predicting the future number of wildfires? So let's take a look at the leading coefficient, which is 9.29. So the leading coefficient is positive, and we have an even degree, which tells us that as time marches on, goes further and further out into the future, we know that the number of wildfires will also increase to infinity. So they'll continue to keep increasing. So now what we have to determine is whether we think this is realistic for making future predictions. And this is always a tough question because, especially for people that are learning, I mean, if we use this model and we even want to go out to say to the year right now, which is 2017, so that would be 21 years. I hope I still have this in my calculator. Yep, I think I do. So I don't have the equation. But if we went out 21 years, this may be like off the charts in terms of the number of wildfires. It's just going to get bigger and bigger and bigger quickly here. So it's probably not realistic if we go too far into the future. And we talked about that throughout the course, that if you go too far outside your data set, then your model can break down. So the end behavior here predicts an unrealistic situation. This is an example of model breakdown. All right, so it's really fantastic for those 5 data points, and probably we might feel pretty good going out a few more years. But beyond that, we probably have to rethink the model. Right, let's take a look now at number 3. The table below gives the number of births in the United States to mothers under 15 years of age for selected years. So from 1960 to 1995 for selected years in that time range. So let's label the axes. We know that the vertical axis is the number of births. And again, let's see how we're measuring time here. So we're starting at 0. And so therefore 1960 is going to be our base year. That's going to be 0. 70 will be 10. 1995 will be 35. Okay. So we've performed 2 regressions here. I'm going to put that over there. In fact, I don't need it. Let's see. Not yet. So we have performed 2 regressions. This is number of years after, what, 1960 we said, right? 1960. We have a cubic regression and a quartic. So this dashed line is our cubic, and the solid curve here is our quartic. Okay, again, how would you know? The quartic has 1, 2, 3 turning points. Therefore, the smallest degree is 4. And with this the cubic here, we've got 1, 2. So therefore, the minimum possible degree would be 3. Both the cubic and the quartic regression models are shown above in the graph. Which graph is which, and which graph appears to be a better fit? Okay, so we just discussed that. This is the quartic right here, this solid curve, the quartic and this is your cubic. So let's change the colors here, cubic. Okay, so which one appears to be the better fit? Again, the quartic looks to be closer to the points given than the cubic. So I'm going to go with the quartic. Quartic model appears to be the best fit. And here's the equation for that quartic right here. Whoa, see how many terms we have? That's why we talked earlier about trying to use the simpler model whenever possible, because the higher the degree, the more calculations you have, and there's other issues too with these higher degree polynomials. I'm just going to replace that f of x there with a y hat. So let's use this Quadratic regression model here to answer the following questions. How many births would this model predict for 1975? Well, 1975 minus 1960 is 15 years. So to predict that, I would put in 15 everywhere I see an x and raise it to the appropriate power. So take a few minutes here and do that. And when you run that through your calculator, you will get about 10,636 births. About, I'm going to put approximately. So how many births would your model predict? The model predicts that in 1975, or you could say estimates, since it's within the data set, either of those are okay, estimates that in 1975 there will be approximately 10,636 births. And we know that those births are to mothers under the age of 15. So, you know, depending on how much time you have and how exact you like to be, which I tend to like to be exact, I would probably complete that sentence with what the data says, right? So I would say 10,636 births to mothers under the age of 15 years. This is all in the United States. All right. So do you feel this model represents the data well? I would say yes, because all the data fall very close to the curve, right? The curve fits the data well. So I would say yes. And again, as long as you have the general idea of what I just said, how you want to write it is really up to you. Okay? It certainly looks like all the data fit very close. Data fits close to Quartic model. Okay, there we go. So let's turn the page and we get a new set of data. This is on the population of Miami, and this is according to the different US censuses from censuses, that's a funny word to say, from 1930 to 2000. So a quadratic regression was performed on this data using the years since 1930 as X and population as Y. So again, I'm just going to put right here my various X values. So if I'm using these values to make estimates or predictions, I have them right here. There we go. So here are my X values. Here's my population. And here's my scatter plot with a quadratic regression model. Write down the quadratic regression equation obtained from the computer and answer the following questions. So y hat equals negative 64.21 x squared plus 8,102.45 x plus 107,091.96. Okay. I'll give you a second to write that down. So do we feel that this model represents the data well? Absolutely. Up to like 1980 area, we don't have any data. Where's our data after that? We have 1990 and 2000. That's right in this area here. Okay. So it fits the data well. The data points that are given. So yes, the data fall very close to the parabola that's graphed, given that model. Okay, so what flaws does this model have? And so let's see what seems to be happening from 1980 on. Let's see, where is 1980? 1980 is 50, right? So 1980 is like right in this area, all right? So after 1980, we're increasing, but then we're slowly increasing, and it appears that maybe we might be leveling off. But our model for 1990 and 2000, for after 2000, our model is going to say that the population of Miami is decreasing, and in the long run, it's going to be negative. That's 140 years out from 1960, right? So 1960, 2000, so about 2100. It's going to be negative, and that's totally unrealistic. So you can see again that we can't be decreasing, we can't be using a model that's going to predict the population going back to zero and eventually becoming negative. So let's take a look at the next page. So now we decided we would try some other models other than the quadratic model, since that didn't make much sense. So we tried a cubic model and a quartic regression on each of these. The solid curve is still the quadratic regression. That's this solid curve right here. This is your quadratic. Okay, that's your quadratic model. The long dashes represents the cubic, so let's make that green. This is your cubic model. And therefore, the little dots here is your quartic regression. And here are the equations for each one of those regressions. So the quadratic prediction, what would be the quadratic prediction for what question? To find the population in the year 2065 for Miami. So 2065 has an X value of 135. And here are the three predictions according to the model. So in 2065, with the quadratic model, you have 30,695 people. With your cubic model, you have 620,246. Oh, 240.6. We'll just call it 240. We could call it 241 if we wanted. With the quartic model, whoa, baby, where are we? 82,007. There appears to be a decimal error here with the let me just see. I'm going to take a look. This number doesn't appear to be right. I mean, this number here is 30,695. My guess is this is 62,024, and there's a decimal error here. So let me just shut off the recording for a second, or pause it, and I will check that out with my calculator. I'll do a little regression, and I'll get right back to you. Okay, I see what's going on here. The error is that this number, the 82,000, should be down here with the cubic model, and the 620,000, this number here, needs to go up there. So that's an error in putting the data values in here. So this should be 620,240.6. Okay, so let's fix that up. And so the cubic model, the minute I wrote that, I knew something was off, because I knew that the distance between those 2 points couldn't be over almost 600,000. And then the quartic is 620,240. Okay. So first of all, in 2065, the population in Miami is going to be down. I don't think so, at least as far as I can tell. The cubic is predicting 82,000. Well, right now, in the year 2000, we're at 362,000 people, so that's not a good model. And the quartic is going to predict that it's almost double what it is in 2000. So none of these models really appear to be very good for predicting the population of Miami, particularly when you look at the end behavior. I mean, this one will continue to increase, which is towards infinity, which isn't really an accurate prediction. Your quadratic is going down to be negative, and then this cubic is going to eventually come back up and increase towards infinity as well. So none of these models appear to work very well for making predictions out to 2065. Okay, so that wraps up the lesson activities for lesson number 22. If you have any questions, please feel free to email me.